Hello, I'm Dr. V. Rapp, and welcome back to Lawrence Berkeley National Laboratory's free video course on laboratory testing of cookstoves. In this lesson, we will be discussing how to measure carbon monoxide and carbon dioxide gases from cookstoves. The objectives of this lesson are to understand how to choose the correct gas analyzer for your lab, how to precondition exhaust samples before they enter your gas analyzer, zeroing, spanning, and calibrating your gas analyzer, correcting measurements for ambient concentrations, and calculating total emissions for an experiment. Before purchasing a gas analyzer, it is important to first estimate the concentration range of carbon monoxide and carbon dioxide you expect to measure in your duct. In most cases, you can estimate the mass emission rate of carbon dioxide and carbon monoxide from the cookstove you plan to test using prior literature or data from similar cookstoves. To convert mass emission rate into duct concentration, we can use the ideal gas law. Concentration is equal to the ratio of mass emission rate, the ideal gas constant, and sample temperature to volumetric flow rate in the duct, molar mass of the pollutant, and atmospheric pressure. For example, we can estimate the duct concentration for a cookstove that will emit about 25 grams per hour of carbon monoxide. Using our lab's duct flow rate of roughly 350 cubic meters per hour sampled at 20 degrees Celsius and sea level pressure, we find that the duct will contain roughly 62 parts per million of carbon monoxide. Remember that this estimate is for the average duct concentration, but your equipment should be suitable to deal with transient spikes that can greatly exceed the average concentration. In our experience, 5 times the average carbon monoxide concentration and 3 times the average carbon dioxide concentration are often safe assumptions for peak concentration, but your results may vary. At our laboratory, we use and recommend purchasing a non-dispersive infrared gas analyzer capable of measuring carbon monoxide and carbon dioxide at different ranges. The multiple operating ranges allow you to accurately measure gaseous emissions from low and high emitting cookstoves. The upper range of your instrument should be capable of measuring carbon monoxide and carbon dioxide of at least 150% of your highest predicted concentration. However, it is important not to dramatically overestimate the pollutant concentrations because as the range of the gas analyzer increases, its accuracy at lower concentrations decreases. As described in a prior video, the duct, blower, and sampling port location should be designed to ensure the cookstove emissions are fully mixed with ambient air in the duct. The sampling line for the gases is inserted into the duct through the sampling port with its opening roughly along the axis of the duct. We recommend that the sampling line's diameter be 5 millimeters or greater, and that the duct sampling line be perpendicular to the duct to help prevent clogging. Moisture and particles in the gas sampled from the duct can damage gas analyzers. To prevent condensation in the gas sample line, ensure that your gas sample remains significantly above the dew point temperature at all times. Follow your gas analyzer's recommendations. If no guidance is provided, we recommend that the relative humidity of the sample gas be less than 70% at room temperature. You can monitor the humidity and temperature in the duct using a thermocouple and a capacitive humidity sensor. The relative humidity of the gas sample can be estimated, assuming the sample is at room temperature, using the relative humidity and temperature in the duct. If the relative humidity of the sample at room temperature is higher than 70%, we recommend further drying the sample. There are several methods for drying the gas sample. The first and easiest method is diluting the humid exhaust in your duct. If your laboratory is located in a dry climate with low relative humidity, simply increase the flow rate through the duct to dilute the humid cookstove emissions with dry room air. This strategy is the easiest and simplest to implement and ensures that the gas and particle samples will not condense at room temperature. However, if your laboratory is located in a very humid climate with high relative humidity, or you are testing a cookstove that generates very high concentrations of water vapor, then you may need to dry the gas sample directly. This can be accomplished using an ice bath to condense water out of the gas sample line, or a desiccant that is non-reactive with carbon monoxide or carbon dioxide. To remove particles from the gas sample, we recommend using an inline HEPA filter, which must be changed regularly. This protects the gas analyzer from damage caused by the particle buildup. If you are using a desiccant to dry your gas sample, the HEPA filter should be placed downstream of the desiccant to prevent desiccant particles from entering the gas analyzer. The gas sampling line and desiccant bed, if necessary, should be kept as short as possible. This will help minimize the time delay between the gas analyzer sample readings and the real-time events with the cook stove, such as lighting the stove or adding more fuel. We recommend that the zero and span also be checked and recorded after every experiment. Please note that when you zero and span your analyzer, you may need to create a manifold to reduce the gas cylinder pressure to the appropriate pressure for your gas analyzer. The manifold can also be used to quickly switch between different calibration gases. Make sure to follow your manufacturer's instructions and guidelines in your gas analyzer manual. We recommend zeroing gas analyzers with a compressed gas cylinder of high purity nitrogen. Span gases are certified concentrations of gas, such as carbon dioxide or carbon monoxide, used to calibrate gas analysis equipment. The exact concentration of span gas is not critical, but it is good practice for span gases to be between 100 and 200% of the average measured pollutant concentration. For example, if you test charcoal stoves emitting about 450 parts per million of carbon monoxide on average, then you would select a carbon monoxide span gas between 450 and 900 parts per million, depending on the certified concentrations available in your region. It is important to note that a span gas should not have the same concentration as your gas analyzer's maximum range. To account for the emissions in the ambient environment, it is important to record ambient concentrations of carbon monoxide and carbon dioxide before and after each test. Currently, the average environmental concentrations of carbon dioxide are approximately 400 parts per million. However, inside a cookstove testing laboratory, people's breath can easily drive the ambient concentrations of carbon dioxide to 1,000 parts per million or higher. This is why it is important to measure concentrations of background pollutants both before and after experiments. The ISO protocols require that background concentrations be measured before and after every experiment. We recommend that a linear interpolation of the pre- and post-test ambient concentrations be subtracted from real-time concentrations measured by the gas analyzer. Alternatively, a better approach is to continuously monitor background concentrations with a second gas analyzer and correct the measured duct data accordingly. To review, the gas analyzer you choose should comfortably accommodate the full range of gas concentrations you expect to measure. Ensure your gas sample is particle-free and that the condensed water will not get inside your gas analyzer. As good practice, you may also want to check the accuracy of your instrument and the data by recording the drift after each experiment. Lastly, correct your data for measured ambient concentrations of pollutants. I'm Dr. V. Rapp from Lawrence Berkeley National Laboratory. Thank you for watching our free video course on laboratory testing of cookstoves.